Okay, and all right, now start the recording. So we're going to naturally cover just a little bit of it tonight, but in this section, they define two operations that can be performed on vector fields that play a basic role in the applications of vector calculus to fluid flow and electricity and magnetism. Okay, so vector calculus is used for fluid flow. It's used as an application for fluid flow and electricity and magnetism. Okay, and so there's a lot of interesting things in section 13.5. But the first thing I want to talk about is something called, what we'll talk about tonight is something called the curl of a vector. So the curl of a vector is defined as you see it here. Okay, this is how a curl, if you have a vector field, the vector field F equals Pi plus Qj plus Rk. It's a vector field in three-dimensional space, and the partial derivatives of P, Q, and R all exist. Then the curl of the vector field is defined by this vector. And it's difficult to remember that vector, all those components. So what they do is they say, okay, well, let's go ahead and define what's called a del operator. Okay, a del operator. And the del operator, okay, it operates on a scalar function to produce a gradient. Okay, so it's an operator. It's an operator. Now, why does this matter to us? Well, let's go back to what the del is defined as, this differential operator. Okay, it's defined as what you see there. Okay, and if we think about if we were to take the cross product of the del operator with the vector field F and put the components of the del operator and the vector field F in the second and third rows of that matrix, and then compute the cross product. So you know how to compute the cross product. How many recall that? Computing the cross product of two vectors, that you set up a determinant and compute a determinant. How many recall that from section 9.4? And you've even seen it. You've seen it recently, but how many recall? Hey, that's how I compute the cross product of two vectors. Is I set up a determinant. Okay. Yes. And so you see, by treating. Thank you, Robin. By defining the curl of a vector field F as the cross product of the del operator and the vector field F, that works. Taking the cross product of this del operator, treating that like a vector, okay, and the vector field F, that will give us the equivalent of what is the curl of a vector field F. So because of that, we can say that the curl of a vector field F is equal to the cross product of the del operator and the vector field. Okay, and so we just apply that cross product, and we don't have to memorize the definition of the curl. Now, there's a very useful theorem here that says that the curl of a gradient, curl of a gradient vector field is equal to the zero vector. Okay, so if we have the curl of a gradient, if the gradient of a function f is itself a vector field, right? So, and it turns out that the curl of a gradient of a function is equal to the zero vector. So because of that, this gives us a way to establish if a vector field in three-dimensional space is conservative or not. Because if they prove this below, but basically, if the vector field, or sorry, I want to get this to show right. If the vector field of your function is conservative, then its curl would have to equal the zero vector, because the vector field f can be written as the gradient of a function, and the curl of a gradient of a function is equal to the zero vector. Okay, so they prove this. They prove this above. They prove this above. Okay, and I think what we'll do is the next class we'll look at that. Right now, I want to do an example real quick. It should only take like 5 minutes to do. Okay, so no, that's not the right example. Sorry. All right, give me the right one. Yeah. Let's look at that. We looked at a problem today where we had a force field. Okay, and the force field was given by this force field. This was the problem we looked at just in section 13.3, where we found the potential function for that force field. But in section 13.3, you were told that you had a conservative, that you were told that this force field was a conservative force field. Okay, so in section 13.3, for the problem involving this force field, you were told it was a conservative force field. What I'd like to do is now let's prove that that is indeed a conservative force field. Okay, so let me give you a moment to copy that, and then we'll go right to the solution. Okay, are there any questions so far before we go to the solution? And you'll notice too that this force field, right, it's not a gravitational force field, right? It's some other force field. I mean, everybody thinks of gravitational force field, and it's a good example of a conservative force field, but there are many, many, many others. And here's one right here. So what we're going to do is we're going to compute the curl of this force field F. And if the curl of that force field F is equal to the zero vector, then that means that this force field F has to be the gradient of some potential function, because the curl of the gradient of a function is equal to the zero vector. Okay, so that's what we're doing here. So okay, let me go to the next page and we'll show it. Okay, so what I do is I say, okay, the curl of the vector field F is defined as the del operator cross the vector field, the cross product of the del operator with the vector field. So I set up the 3 by 3 determinant, where the second row is treated as the components of the second row are the components of the del operator, and the components of the third row are the P, the Q, and the R components of that of our force field. Okay, and so all we do is we do the determinant of a 3 by 3. So the determinant of a 3 by 3, for instance, if we block out the first column and the first row, then to get the determinant, right, we do the cross product of this part right here, right? This, let me just, hold on. Yeah, we do the determinant of, get that in blue so it shows a little better, the determinant of this 2 by 2 matrix, and we do the cross product. So really what you're doing then is you're doing the partial. So this looks like, I mean, you're like multiplying, but you're not multiplying. You're taking the partial derivative of 3y e to the 3z power with respect to y minus the partial derivative of 2xy plus e to the 3z power with respect to z. And then you're subtracting, right? But it's kind of like you're thinking, oh, it looks like multiplication, but it's not. You know, it's just a way to remember how to get the curl. And we do the same thing for the other two pieces, okay, of the determinant. So think of it, it's like, oh, it looks like multiplication here, but it's not multiplication. You're taking partial derivatives. It's just a way to remember to do it. It's like scuba. Think of scuba. Scuba stands for self-contained underwater breathing apparatus. Well, this is how we're going to remember how to compute this curl, right? And so when we work it out, we're going to end up getting the zero vector. When we take these partial derivatives, okay, we'll end up getting the zero vector. And so that shows that this vector field F is a conservative vector field. Okay, that shows that. And that's how this works. So I appreciate, I went over just a few minutes here on time. I appreciate you're all staying like you did. Thank you. Are there any questions? Okay, who's feeling reasonably good with what you're seeing here? Who's reasonably comfortable? Thank you. All right, Christopher, excellent. Ryan, very good. And Eric, okay, great. So of course we have a lot more to talk about with section 13.5, but at least you know you've seen a little bit of it. And on that note, I'll stop the recording.